Welcome. This is complex analysis, third session on Lurents series. In the last lecture we proved if I have a holomorphic function in annulus, okay, then we said that integral f going to integral f over gamma r, that is a path, that is a constant, okay, and we want to derive its consequences in this lecture. Alright, so what we had, so A is an annular region R1, R2, and F is holomorphic from A to C. Then we said if for any R between R1 and R2, let us look at gamma R of T to be A plus R e power I T, then integral, okay, R going to integral or gamma R of this path is a constant. Okay, now let's try to prove. You shall use this, okay, to prove a Cauchy type formula Cauchy integral type formula for F which is holomorphic on the annular region. Okay, just it will be worthwhile to recall if we saw that if you use a domain and f is a function and fix an a in u, said that br is contained in u, then we said that for any 0 less than r, okay, we have a Cauchy integral formula, namely f of z equal to 1 by 2 pi I integral f of w by w minus z for all z in BR. Okay, this is our Cauchy integral formula. Okay, now we want to get a Cauchy integral formula for function holomorphic on the annular region. Okay, so do you recall how we got this? Okay, how did we get? We looked at the function g of w or f of w to be little f of w minus f of z by w minus z and equal to f prime of z. Then this function capital F, okay, this is a function which will be continuous on u minus z, sorry, continuous on u and holomorphic on u minus z, but then by an extension of Cauchy-Goursat we know f is holomorphic, and we applied, therefore integral of f over gamma r should be 0. This is over gamma r. Okay, then we for w in gamma, okay, and z not on gamma, we saw then the formula is capital F of w equal to fw minus fz by w minus z. Use the linearity of the path integral and we got the Cauchy integral formula. So did you see what I did? Actually we went through the proof of Cauchy integral formula here. This is what I want you to do. When you learn something, when you have to use something, quickly go through it. Don't work out all the details if necessary. Okay, but go through the proof. Therefore, the idea is very clear. Then you have the confidence. You can work on the minute details. Okay, rigorous proof. You can fix it earlier. This is a trick you have to learn if you want to master any subject. Okay, let's go back. So I want to define the same thing here. Okay, so let wz be in the annular region. Okay, then define f of w to be f of w minus f of z by w minus z when w is not equal to z and equal to f prime of z. Okay, then as I said earlier, by extension of Cauchy and okay, Run, if you want to look at now, you can also use Raymond's theorem of singularity, removal singularity. Therefore, f from A to C is holomorphic. Notice this f depends on z. Okay, so actually f is a function of two variables, but we are concentrating only on z. Is that okay? Right. Now, since f is holomorphic, then we know, okay, so you fix R1 less than R2 less than R2, right? Then we know that, let me call it gamma 1 is gamma R1, gamma R1, gamma 2 is gamma of R2. And what is gamma R? Gamma R I already defined. Gamma R of t is A R e power I t 0 less than equal to t less than equal to 2 pi. Okay. Then what we saw in the last session is integral of capital F over gamma 1 is same as integral of F over gamma 2. Okay. So what now we want to do is we want to unwind the definition. Okay, right? Now I am going to take, so for this matter, so let us take this z to be, so that mod z minus a is less than R2 less than R1. Okay, so if you want given z, choose R1 R2 so that this happens. Are you following? Okay, now let us look at, so now notice that z is not going to be on gamma 1 and it's not also going to be on gamma 2, because on gamma 1 if it is there then it should be equal to R1, and similarly if it's on gamma 2 it must be equal to R2. This is not the case, right? Therefore therefore f of w is going to be fw minus f of z by w minus z for every w on gamma 1, and similarly gamma j in fact, right? Therefore let us find out let us compute what is f of gamma 1. Therefore that is going to be f of w by w minus z minus f of z by w minus z. If you want to put dz you put, but usually sometime I may not do that, gamma 1. But we know that path integral is linear, therefore this is nothing other than, okay, integral of f of w by w minus z dw over gamma 1 minus, remember z is independent, therefore it's gamma 1 by dw by w minus z. Now let's look at what kind of thing we have. I have this and I have this. Okay, this is gamma 1, this is gamma 2, my z is here and my w is here, right? Therefore this is nothing other than, okay, if I want to take 1 by 2 pi I of integral f over gamma is 1 by 2 pi I and 1 by 2 pi I of this. Okay, but this 1 by 2 pi I of this is nothing other than the winding number of gamma 1 around z, but z is outside the disk, therefore I know this fellow is equal to 0, right? Therefore what I get? I got 1 by 2 pi I of integral over gamma 1, sorry, gamma 1 is 1 by 2 pi I of integral fw by w minus z dw. So pause, review, proceed. Okay, now it's a child's play to do this. 1 by 2 pi I of f over gamma 2, as we said earlier, 1 by 2 pi I of f of w by w minus z dw minus 1 by 2 pi I f of z. Let me put f of z here so that I will recognize this. 1 by 2 pi I integral over gamma 2, this gamma 2 of yeah, dw by w minus z. Alright, now notice that where is my z? My z is in b a r2. Therefore this is the winding number of gamma 2 around z, but it winds around 1. Therefore I know this is 2 pi I, right? Therefore I know this is just f of z. This fellow is 1, this is equal to 1. Therefore what I have is 1 by 2 pi I of integral capital F over gamma 2 equal to 1 by 2 pi I integral over gamma 2 of f of w by w minus z dw minus fz. This is 2, right? Yeah, but we know this integral is same as 1 by 2 pi I of integral f over gamma 1, and that I know that integral is nothing other than 1 by 2 pi I integral over gamma 1 f of w by w minus z dw, this one. Therefore if I can equate these two, therefore I get a formula for fz. Therefore f of z equal to, okay, these two are equal, therefore take f of z to the left side. Therefore this is integral over gamma 2 minus integral over gamma 1. So I have 1 by 2 pi I integral over gamma 2 of f of w by w minus z dw minus 1 by 2 pi I integral of f of w by w minus z dw over gamma 1. Okay, this is Cauchy integral formula for an annulus. Right? So is that easy? So you should appreciate. You see that this is one of the reasons I want you to learn things thoroughly rather than learning for exam purpose. Once you have learned, you see, you begin to enjoy. You see, it's the same kind of argument we are repeating. Okay, so it becomes, life is more easier, right? That's it. Now let's try to analyze this. So this AIF, may call it star so that it will be easy. I will write f of z, okay, as f2 of z plus f1 of z. Therefore f2 of z is this fellow, and f1 of z is this fellow, including the minus sign. Right? Okay. Now do you remember in the last lecture I talked about Laurent decomposition? F of z will be written as something like f2z plus f1z with f2 and f1 having some properties. We want to check that. Okay, that's very easy. Now let's look at this. The first one, the blue integral, okay, f2, okay, this is holomorphic on c minus gamma 2 and hence in b of a r2. Why? Because f is continuous function on gamma 2. This is the Cauchy type integral we had already discussed. Any Cauchy type integral is actually analytic and hence holomorphic outside the track, right? Therefore we know this is the case. So in particular it is holomorphic on b a r2, right? Okay, now let's look at f1. Okay, f1 of z is going to be with a minus sign 1 by 2 pi I integral of f of w by w minus z dw over gamma 1. Therefore this is again analytic. Okay, outside, okay, this is analytic or holomorphic. We know it's analytic. I am just writing outside the closed ball BA R1, right? So let us recall. I hope all of you remember the thing. So I have this and I have this. Okay, this is my A. Okay, so this is holomorphic. So this fellow is going to be holomorphic everywhere. Sorry, I should have used this. This is my F1. Okay, my F2 is holomorphic here inside the bigger disk, right? Therefore what do I get? Therefore I proved whatever we wanted. That is, I got the thing. The next thing I want to prove is, okay, f1 of z goes to 0 as z goes to infinity. This is what I want to prove, right? That is very easy. See, but for sine, let us look at this. This is going to be integral of gamma 1 f of w by w minus z dw. And remember, mod f on gamma 1 will be less than or equal to some constant on gamma 1. Okay, it's a continuous function, therefore it's bounded. Okay, but remember, by w is fixed. Okay, so what I know is w minus a. So mod w equal to less than or equal to mod w minus a plus mod a. Therefore this is, okay, this is we know is equal to r1 plus mod a. Okay, so this fellow is bounded. Okay, but w minus z modulus, okay, is greater than or equal to mod z minus mod w, right? Therefore as z tends to infinity, this goes to infinity, right? Therefore by ML inequality, okay, modulus of this integral f of w by w minus z dw over gamma 1 will be less than or equal to length of this. I know what is length of this, something like 2 pi r1 and into m into something which goes to 0, right? That is going to be greater than or equal to mod z minus r1 minus a, perhaps. Okay, I hope I'm correct. This goes to 0 as mod z goes to infinity. So right, this may not be very correct, so let us be very careful. Less than or equal to 2 pi r1 by m, and let's just say simply mod z. Okay, so I can put an estimate for this mod z minus, okay, mod of z minus w. I can write it as, I want greater than or equal to mod z minus mod w. Okay, that's good enough for me. And but mod w, I want to get an estimate for that. Mod w will be again I want greater than or equal to, therefore let me write, okay, mod w minus a is less than or equal to mod w plus mod a. Therefore mod w is greater than or equal to mod w minus a by mod a in modulus, whichever is bigger, therefore it is bigger. Okay, and this is greater than or equal to r1 minus mod a, right? Therefore that will be like, so, okay, so you have an estimate 1 upon mod z minus w will be less than or equal to something like 1 upon mod z minus this fellow r1 minus mod a or some such thing. It goes to 0 as mod z goes to infinity. Okay, I may be a little confusing. Okay, but let's just you check it on your own. Okay, the trick is I am looking at mod z minus w, but mod w is going to vary over a compact set and z goes to infinity. You understand that? Therefore, this will be, are you following? Okay, this goes to infinity as z goes to infinity. That's all we needed. So, what I have finally proved, so I finally got the following result, namely f, which is holomorphic and the annular region, I wrote it as f2 plus f1, f2 holomorphic in at present BAR2 and f1 holomorphic outside BAR1, and it is unique, and f1 of z goes to 0 as z goes to infinity, and we know this expansion is unique, right? But let's understand it more. Pause this, go through this, make sure that you understand. Okay, so the next thing I would like to ask is something. See, this is true for every r1 less than r2 less than r2, right? And notice that if I have some other s1 less than s2 kind of thing, okay, right, then depending upon r, s1, etc., okay, these functions, let me call it f2r, f equal to f2r and f1r, this is r for r1 and equal to f2s plus f1s for this s1 notation. Okay, these are all unique. Okay, so whatever is the common domain, so I have a common domain r1 less than mod z minus a less than r2 and s1 less than mod z minus a less than s2. Okay, so there are two annular regions around a, so you just intersect. Whatever is the common thing, because of the uniqueness, these fellows must be equal on the common domain. Okay, therefore this result is true for every r1 r2 as above, and hence I get actually we in fact get f2 holomorphic outside inside BAR2 and f1 holomorphic outside BAR1, and such that f1 goes to 0 as z goes to infinity and f equal to f2 plus f1. That is, we found a Laurent decomposition on the entire annular region. These are all very subtle things, but it's worth learning because, okay, R1 or arbitrary at our arbitrary disposal. Okay, in that annular region, I got a Laurent decomposition, but because of uniqueness, okay, I can change the annular region, but still all of them will patch together. Okay, right? They will agree upon common domain. Therefore, I get a single holomorphic function on the entire annulus. Two such things, f2 and f1. Okay, please think over, don't rush through these things. Please go through that. These are all very subtle points. Usually one just does computation then leaves it at that. We did something much more carefully. Please go through it. Okay, now once we do you remember how we got a holomorphic function is analytic? Once we got Cauchy integral formula, okay, the denominator, okay, we manipulated so that we can get a geometric series. That gave us a power series expansion in powers of z minus a for the function f. That is why we proved it's analytic, right? So here also we are going to do, but except That's a major point. We are going to get powers of z minus a, that is z minus a to the power n, but n may also turn out to be negative. So for all n in z, we are going to get a power series expansion. Something like f of z in the annular region will be summation cn z minus a to the power n, where n runs from minus infinity to plus infinity. Okay, the proof is exactly similar to the way we proved analyticity of a holomorphic function after the Cauchy integral formula. Okay, just to take a break and try to see whether you can work out and apply that to our f equal to integral over gamma 2 minus integral over gamma 1, and what kind of geometric series you see that. Okay, that will be fun. Okay, we will do it next, but you should try on your own. Now let us see how to use our Laurent decomposition to write f of z, to represent f of z as a power series with negative powers z minus a to the power n, where n is allowed to vary over all integers. Okay, that will be called Laurent series. So let us continue. Okay, so we have f of z equal to 1 by 2 pi I integral over gamma 2 of f of w by w minus z dz minus 1 by 2 pi I integral over gamma of f of w by w minus z dw. Okay, right. So the way we want to get the power series is exactly the way we derived the power series expansion from the Cauchy integral formula for a holomorphic function. The trick is, as I keep saying, always to use geometric power series. So let us look at this. So we have two circles, the big circle, okay, and then we have a smaller circle. Okay, so various radii, right? Our annulus is going to be something in between. Whatever is inside is our thing. These are annulus. Okay, so this is your gamma 2 and this is your gamma 1. This is the radius is, I think, r2 and r1. Okay, right. Now if z is here, see, now z is here, right? Therefore what do I know? This is your point A. Therefore I can see that w minus a will be greater than z minus a, right? The distance of z to a will be less than the distance of this. Therefore we do this standard trick, namely we write down w minus z as w minus a minus z minus a. Since w minus a is bigger, so I can take w minus a outside, 1 minus z minus a by w minus a, right? And since mod z minus a by w minus a is less than 1, right, I can use a geometric power series to write this as, therefore 1 upon w minus z I can write as 1 upon w minus a into 1 minus z minus a by w minus a. That will be equal to 1 by w minus a into z minus a to the power n by w minus a to the power n, and n running from 0 to infinity. So that is equal to 1 by, okay, so z minus a to the power n by w minus a to the power n plus 1, n equal to 0 to infinity. Again, as usual, you know that this series, geometric power series, is uniformly and absolutely convergent. Uniformly, and it's absolutely convergent on the entire thing. Okay, but this is going to be uniformly and absolutely convergent on any kind of compact sets. right? In particular, on gamma 2 it will be uniformly convergent. Therefore 1 by 2 pi I integral over gamma 2 f of w by w minus z dw I can write as 1 by 2 pi I integral gamma 2 over this sum. Okay, let me write f of w into the sum n equal to 0 to infinity of z minus a to the power n by w minus a to the power n plus 1 and dw. Right? And again remember, this is uniformly convergent on compact sets, and this is going to be bounded function on gamma 2. Therefore this times this as a function of w, namely w going to f of w into this series. Okay, this will be uniformly convergent on gamma 2. If f1 converges to f uniformly and g is bounded, then f and g converges to fg uniformly, etc. So many times we have used it in our course, so you should know this. So I can interchange the summation and the integral. Therefore what do I get? I will get the summation n equal to 0 to infinity of integral 1 by 2 pi I of integral f of w by w minus a to the power n plus 1 over gamma 2 into z minus a to the power n, because z minus a to the power n is independent of the integrating variable w, right? So this I can write as summation n equal to 0 to infinity cn z minus a to the power n. This is exactly the same proof we have seen. I am just repeating so that you will feel comfortable. 1 by 2 pi I integral over gamma 2 of f of w by w minus a to the power n plus 1 dw. If you want, put a dw here also. Okay, so this is about f2. Now let's look at f1. Yeah, so I have minus 1 by 2 pi I integral over gamma 1 f of w by w minus z dw. Now let's go back to our picture. My z gamma 1 is this now. Therefore z minus a will be, this distance will be bigger than this distance. This is w, right? Therefore here when I try to write w minus z with the same trick as w minus a minus z minus a, notice that mod z minus a is bigger than mod w minus a. Therefore what should I take out? I should take out mod z minus a out. When I take mod z minus a out, I have w minus a by z minus a minus 1. So this is going to be minus of z minus a, right, into 1 minus w minus a by z minus a. As usual, I can write the geometric power series expansion, which is again uniformly convergent, etc., etc., on gamma 2. So let us do that. Therefore 1 upon w minus z equal to minus 1 upon z minus a into summation w minus a to the power n. Let me write it as k now. K equal to 0 to n, 0 to infinity by z minus a to the power k. So this is going to be, there is a minus sign. Okay, w minus a to the power k by into z minus a to the power k minus 1, and k running from 0 to infinity. Is that okay? Therefore what I have, 1 by 2 pi I integral over gamma 1 of f of w, this is a minus sign, by w minus z dw, and this minus sign and this minus sign cancels, and as usual uniform convergence over compact sets will allow me to interchange. So I will get something like k equal to 0 to infinity of 1 by 2 pi I integral of f of w into w minus k into z minus a to the power minus k minus 1. Is this okay? Right? Now what I want to do is I want to write the power series. Therefore f of z is f2 of z minus f1 of z. So f2 of z I already saw something like cn z minus a to the power n, where n is from to 0 to infinity. The other one I want to write as some other c. Okay, this is again cn z minus a to the power n, where n equal to minus 1 to minus, if you want, minus infinity to minus 1, or whatever it is, or n equal to 1 to infinity with a minus sign. Okay, I want to write this way. So let us try to do change of variables. So in this I put n equal to minus k minus 1. Therefore, yeah, so n equal to minus of k plus 1. Yeah, therefore n, so this is n plus 1 equal to minus k, right? N equal to minus k minus 1, bring this minus 1 to this side, n plus 1 equal to minus k. Therefore my k is going to be, so this now becomes, and also when k equal to 0, n equal to minus 1, when k equal to infinity, n equal to minus infinity. Therefore this sum I can write as n equal to minus infinity to minus 1 of integral 1 by 2 pi I integral over gamma 1 of f of w. Now remove w minus k, therefore this is k, therefore k equal to minus of n plus 1. Therefore I can write it as w minus a to the power n plus 1, and this becomes into z minus a to the power n. Just pay attention, just make sure you are comfortable with this, right? Therefore I can now write f of z equal to f2 of z plus f1 of z for all z in the annular region. Okay, summation cn z minus a to the power n, where n equal to minus infinity to plus infinity, where cn, notice that it's always given by the same formula, exactly like the formula you got it. And this is true for every n in integer. So if notice that if not only for n greater than or equal to 0, for n negative also the same integral formula for cn holds. Okay, but then there is a slight subtlety. If you are careful, you will say for n positive my cn should be taken over some gamma 2. Okay, for n negative you have to take over gamma 1. So how can I write like the same thing with the same gamma? But let us look at, fix any r which is between r1 and r2, or capital R1 and capital R2, if that's a thing. Okay, now this function f of w by w minus a to the power n plus 1, this is function w going to this is holomorphic and the annular region, right? Therefore we know the integral over gamma r will be the same as integral over gamma 1, which will be integral over gamma 2, etc. of this, whatever this object, right? Therefore what I have is f of z equal to summation cn z minus a to the power n, where n is from minus infinity to plus infinity, where cn is always given by 1 by 2 pi I integral over gamma r f of w by w minus a to the power n plus 1 dw, where r is between r1. So this is called the Laurent series. In the annular region. So pause, review, proceed. Okay, right. Now we want to use this to understand isolated singularities. Therefore, let's look at my function f, which is holomorphic on BA R to C. Therefore, my R1 I can take it as 0 and R2 I will take it as R, right? Right. Therefore, I have a Lurents series here, which is again Cn z minus a to the power n. N is from minus infinity to plus infinity, where Cn is given by 1 by 2 pi I integral over gamma r f of w by w minus a to the power n plus 1 dw, where r is between r and 0. Alright. So our idea is to understand the nature of the isolated singularity of f at A in terms of Lorentz series. As I said when I define the Lorentz series, most often textbooks derive the Lorentz series and then define isolated singularities, classify the isolated singularities. We are going the other way around. Okay, because isolated singularities, as we saw, depends only on the nature of the limit z tends to a f of z, how it behaves. Depending upon that, we had classified isolated singularities. That is much more natural and easier way. Here you can see how much we have to work to get this. Yeah, okay, good. So the first question is, suppose f is actually has a removable singularity. Or f is actually holomorphic on BR. Notice that whenever I have a removable singularity, that means I can define f of a suitably so that f becomes holomorphic on the disk under consideration, right? Therefore I can ask, and it is same as saying f is also bounded. Then f is going to be bounded on some interval, let us say BA delta, where delta is less than r. Okay, this is same as saying limit z going to a, or f is bounded in neighborhood in a punctured disk around a. All these things are equivalent, we have seen already. This is essentially Riemann's theorem of removed singularity. Okay, now because it has removed singularity, again I can say this is going to be something like n equal to 0 to infinity c n z minus a to the power n, and plus n equal to minus into minus 1 c n z minus a to the power minus n. But if it is holomorphic, okay, we know then I have a power series expansion z minus a to the power n, which is valid in the maximum possible open disk contained in the domain of f. Right? You understand that? See, therefore, now the problem is, so what should I guess? I should guess this must be 0. Okay, this is my guess. Okay, this part is called the singular part or the principal part. Or principal part. These are just some name, somewhat archaic, old-fashioned name. It's still used, so it may be better to have that. The negative part of the series is called singular part or the principal part. So in the case of removable singularity, I should expect the singular part should be 0. This is my expectation. Okay, can I prove that? Okay, notice that this is nothing other than our f2 of z plus f1 of z, right? Okay, therefore what I want to say is f1 is 0, right? But remember, we had already done, suppose f is holomorphic, then I can write this as f of z, okay, plus 0. See, my f1, this f1 part should be a holomorphic function vanishing at infinity, but I am saying it is actually 0, right? Therefore, by the uniqueness of the limit, uniqueness of the Laurent decomposition, implies my f1 is actually 0 and f2 is f1. f2 is f. Yeah, don't you think this is a very cute proof? Okay, yeah, but there is a standard way many people write is by using the so-called Cauchy's estimate. Right, now let's look at what is Cn. Cn is 1 by 2 pi I integral over gamma r f of w by w minus a to the power n plus 1 dw. Right, so it's enough. Therefore mod Cn, notice that, so f of w will be bounded by mr on gamma r. Right, therefore mod Cn is less than or equal to 1 by 2 pi a into 2 pi r into m by r to the power n plus 1. This is true for all n, independent for all integers. Okay, this is the way we have applied Cauchy's estimate when in the case of Cauchy integral formula for holomorphic functions, but this is just ML inequality, right? Therefore I get it. Now the interesting thing is, remember, see, we are assuming, suppose BA delta is contained in BAR, right, and as suppose m is the upper bound mod f. Okay, mod f is less than or equal to m for all on B, the closed and bounded disk, because remember f is holomorphic and hence continuous, therefore mod f will be bounded on that. Right, therefore let me assume my r is less than delta and r goes to 0. Right, therefore this is equal to 1 by 2 pi, and then there is a 2, this 2 pi also get cancelled. I hope I am doing it correctly. Okay, 2 pi and m by r power n. Right, but remember, if n is negative, right, then what I have is mod Cn is less than or equal to m into r to the power minus n, because r to the power n I can bring as n, but therefore minus n is positive now, and I can let r come to 0. This goes to 0 as r goes to 0. This is remember, this is true for each and every r less than right, because our formula for Cn is independent of which r I chose, that we had already seen. Therefore this goes to 0 there. Now notice that we used n is negative here, right? Therefore all my C, if for every n negative, my Cn is 0. Therefore the singular part is 0. If A is a removable singularity. Okay, so go through this proof. So in the next session I will use Lurents series to classify isolated singularities. That will be more or less the end of the Laurent series, but for one or two things. See, usually, as I keep saying, complex analysis, complex calculus. The conceptually complex analysis is a little more challenging and difficult because there are so many ideas involved, and the proofs are not very straightforward. It's a zigzag manner, or what I call bootstrap kind of argument. Involved arguments are used. Okay, so many times people give okay, look at this function with isolated singularity, write down the Laurent series here in this annulus, in that annulus, etc. So perhaps I will also do one sample case. The rest of the thing you can read from my book or from other textbooks available with you. Okay, I think that's so. We will meet again. This is okay. Take care. Stay safe.